Now we're going to look at the graph data structure. And to understand the graphs, they are an essential data structure, of course, and they used to model relationships between objects. So we apply them widely even in real life. They are applied in spaces such as networking, heavily applied in social media, in navigation systems, and many, many more, even ride sharing and all that. So, just to start with some definitions here, a graph itself consists of two things. It consists of vertices, which you also refer to as nodes, and it also consists of edges, which we also refer to as arcs. And the difference between the two is that vertices, as you can see, these are the vertices here that represents these data points, and the edges represent the connections. Right? So we can just think of them as we have two sets of points, and there are lines that are connecting those sets of points. Some real world applications of this is, for example, in social media. So we have social media application. In a social media application, each person is considered as a vertex, and each friendship that person has online is an edge. So if we have person A and person B, A and B, a vertex, they refer to a vertex basically, and vertices in plural, and then the friendship between person A and person B, we refer to that as an edge. Or you can also think of it when you're looking at a map. We have point A and point B, or city A and city B. So the roads that are connecting city A and city B are what we refer to as edges. Yeah. So assuming this is city A and this is city B, this distance here is what we refer to as edges. So the two key terminologies are the ones that we've already talked about. We have vertices and we have edges. So vertices, they are unit in the graph that represents basically the entities or the objects that we talk about here. So, for example, in our cases here, we have 12. This 12 qualifies as a vertex. Then the line between, let's say, 12 and 4, that is an edge. Yeah. So as you can see here, and think of an edge again as just a friendship or connection between two or more people. Now, we do have graph representations that we follow, and we have like an adjacency matrix and an adjacency list. And just the difference between the two, I'm just going to write them here. So we have an adjacency matrix, and we also have an adjacency list. So starting with an adjacency matrix, so an adjacency matrix, think of it like maybe a 2D array where rows represent vertices and columns represent basically vertices, right? So if an edge exists between two vertices, then the corresponding matrix entry is marked. And we often use zeros and ones. So it look like this, just the rough representation. So you have, maybe this is a matrix here, and we're representing a number of elements here, and we also have them up here. So here we're going to represent the relationships with a one. So if there's a relationship between, let's say, this point and this point, we just mark it with a one. And if there's no relationship between this and any other points, we're going to mark those with zeros. And we're going to see how we can do this adjacency matrices in a moment as we progress. So we also have an adjacency list, and in the adjacency list that we see here, this is basically where each vertex has its own list of connected vertices or nodes like we've seen. And instead of using a 2D matrix, it stores only the edge of each vertex. So how that would look like, it would look like this. Let's say we have vertex 1. So let's say we have vertex 1 here, and it has a connection, in here we just have a list that has maybe element 2 and 3 or 2 so this means that vertex 1, this means that the vertex 1 here is connected to the vertices 2 and 3. So that is when we decide to use an adjacency list. And on top of these graphs as well, we have different types of graphs, and we can look at two other types. So we have directed and undirected graphs. We can just have that text down here. Let's actually have it in white. So here we have directed, and we also have this is verses, and we have and undirected undirected graphs. There should be an I. So we have directed and undirected graphs. And when you talk of something like undirected, yeah, it looks okay. So when you talk of undirected graphs, basically undirected graphs, uh, the edges have no direction. When that's why we refer to them as undirected, right? And basically the edge between a vertex, let's say 4 here, and a vertex 7 can be traversed in both directions. So as you can see, between 4 and 7, there's no specific direction when it comes to the edge that is connecting them. So for example, in a social network, if you have in a social network, you'd have maybe person A, and then you have person B, right? Then if person A is friends with person B, so there's a connection between this. If person is a friend with person B, then person B is also a friend with person A. This is when we have an undirected graph. So there's a friendship between, since you can traverse across A and B. Then we now have directed graphs, which are basically the opposite of a directed graph. And here, each edge has a direction. So all these edges that you can see here, each of them has a direction. So if there's a directed edge from, let's say, vertex A, let's say we just remove that arrow like that. So if there's a directed edge between vertex A here and basically to vertex B, you can only move from A to B. That is, you can only move to the direction that the arrow is showing you, and you can't move the other way around. So an example here, an example that we can use here is when you go on a platform like X. So when you go on a platform like X, basically you can follow a person A can follow person B, but it doesn't necessarily mean that person B follows person A back, right? So that is what we refer to as in a directed graph. So if the example graph that we have here, this is undirected, but if it was a directed graph, then you'd see arrows here pointing to different directions, basically to show the relationships between these vertices or the nodes that we have here. So I'm just going to remove those for now. Then we also have other types of graphs. We have what we refer to as weighted. So we have weighted. This should be, yeah, like that. So we have weighted and unweighted. We have weighted and unweighted graphs. There should be G here. Yeah, so we have weighted and unweighted graphs. And the major difference between the two here is we can start with the weighted graph. So, or rather the unweighted graph. So for the unweighted graph, all edges have the same significance. What this means is that there's no edge that is more important than the other. So for example, if this is an unweighted graph, then all of these edges, they're basically have the same significance. So this could be in terms of, let's say, the size of the edges. So if each edge is given a size of 1, then all of the other edges that exist here also have a size of 1, right? So all of them have a size of 1. That is simply what a weighted graph means, or rather an unweighted graph. But when you talk of a weighted graph, so in let me just remove all this. When you talk of weighted graphs now, each basically the edges that we have, each of them has weights or costs that are associated with them. So for example, as you saw, I was assigning each of them some sort of weight or significance, right? So that is what we refer to as weighted graphs. They have certain weights associated to them or certain costs. And these weights can represent a number of things. So, for example, it can represent distance, it can represent time, or any other resource that we decide to represent it with. So, for example, if we're in a road network, and let's assume this is a road network that we have here, the weight might represent the distance between the cities. So if you have city 12 to city 5, then it has some distance. So let's say the distance is about 50 miles, then the same now could apply to some of these other. So this could be maybe 10 miles, and it applies and so on and so forth to all the others. So basically, each of them has a weight or a cost that has been attached to it. And the number on the edge between A and B just represents that weight that we've decided to give that. So, and that is what a weighted graph is. And yeah, so there are also many other different types of graphs that you can go and find and look at, but these are some of the main ones, right? So now we've also looked at how you can represent maybe like an adjacency matrix, right? So an example that you could do here is, let's say this the 7 and 10. So we have they have maybe some direction to them like that. So 7 is pointing to all these others here, and maybe 10 is pointing there, 7 is pointing here. So like this. So let's say these are directed graphs, and we want to build an adjacency matrix here. So what we'll do is we're going to have matrix representation here. Then we'll represent all of them. So let's say we have 4, then we have 7, then all the others following down basically. Then up here we also do the same. We have 4, we have 7, and all the other elements, all the other vertices rather, they will also represented there. So what you look at when you're building adjacency matrix is in terms of direction, if there's a connection, right? So if you're talking about 4 and 4, clearly those don't need to be connected, so you give them a 0. But 4 and 7, there's a connection there, so we can give this a 1. Then let's say we had maybe something like 10. Let's say we had 10 somewhere here as the other element. So we have 10 here. So between 4 and 10, there's no connection between 4 and 10. So that will also be a 0. Then 7 and 4, there's no connection. This is one direction. So we also give it a 0. And then 7 and 7, we give it a 0 as well. And 7 and 10, we give it a 1 because there's a connection, as you can see here. And that is basically how you build an adjacency matrix when you're dealing with a graph. You can go on and on about all the other elements. But ideally, that is it. We've introduced graphs, and we've seen how they consist of vertices and edges. And we've looked at some common ways that we represent graphs. So we've looked at the adjacency matrix, and we've also looked at adjacency list, which is the what you looked at here. And we've also discussed some different types of graphs. We have directed graphs, undirected graphs, weighted graphs, and unweighted graphs. Yeah, and that is it. So next we're going to go in the next session, that is, we're going to go and look at uh, graph traversal algorithms. So we have algorithms like breadth first search and depth first search, and they're going to be really exciting. Thank you, and I'll see you then.